Structure and interpretation of computer programs, bite size. 1.3.4 Procedures as returned values. In the above examples demonstrate how the ability to pass procedures as arguments significantly enhances the expressive power of our programming language. We can achieve even more expressive power by creating procedures whose returned values are themselves procedures. We can illustrate this idea by looking again at the fixed point example described at the end of section 1.3.3. We formulated a new version of the square root procedure as a fixed point search, starting with the observation that the square root of x is a fixed point of the function y maps to x over y. Then we used average damping to make the approximations converge. Average damping is a useful general technique in itself. Namely, given a function f, we consider the function whose value at x is equal to the average of x and f of x. We can express the idea of average damping by means of the following procedure. Define the procedure average damp that takes input f to be the lambda the procedure that takes input x and returns the average of x and f of x. Average damp is a procedure that takes as its arguments a procedure f and returns as its value a procedure produced by the lambda that when applied to the number x produces an average of x and f of x. For example, applying average damp to the square procedure produces a procedure whose value at some number x is an average of x and x squared. Applying this resulting procedure to 10 returns the average of 10 and 100, or 55. So average damp square 10 is 55. Using average damp, we can reformulate the square root procedure as follows. Define the procedure square root that takes input x to be apply fixed point to average damp applied to the lambda of y and x over y, and then 1 is the other input. Notice how this formulation makes explicit the three ideas of the method: fixed point search, average damping, and the function y maps to x divided by y. It is instructive to compare this formulation of the square root method with the original version given in section 1.1.7. Bear in mind that these procedures express the same process, and notice how much clearer the idea becomes when we express the process in terms of these abstractions. In general, there are many ways to formulate a process as a procedure. Experienced programmers know how to choose procedural formulations that are particularly perspicuous and where useful elements of the process are exposed as separate entities that can be reused in other applications. As a simple example of reuse, notice that the cube root of x is a fixed point of the function y maps to x divided by y squared. So we can immediately generalize a square root procedure to one that extracts cube roots. Define the cube root of x to be the procedure cube root that takes input x to be the fixed point applied to 1 and average damp applied to the lambda of y applied to x divided by the square of y. All of that. Alright. Newton's method. When we first introduced the square root procedure in section 1.1.7, we mentioned that this was a special case of Newton's method. If x maps to g of x is a differentiable function, then the solution of the equation g of x equals 0 is a fixed point of the function x maps to f of x, where f of x is equal to x minus g of x over dg of x. And dg of x is the derivative of g evaluated at x. Newton's method is the use of a fixed point method we saw above to approximate a solution of the equation by finding a fixed point of the function f. For many functions g and for sufficiently good initial guesses for x, Newton's method converges very rapidly to a solution of g of x equals 0. In order to implement Newton's methods as a procedure, we must first express the idea of a derivative. Note that derivative, like average damping, is something that transforms a function into another function. For instance, the derivative of the function of x maps to x cubed is the function x maps to 3x squared. In general, if g is a function and d of x is a small number, then the derivative of d of g then the derivative d of g is the function whose value at any number x is given in the limit of the small dx by d of g of x equals g times x plus d of x minus g of x all over d of x. Thus we can express the idea of derivative by taking d of x to be, say, 0.00000001 as the procedure. Define the procedure deriv that takes input g to be the procedure that takes input x, that is, you apply dividing to these three terms. D of x, g times x, and then this. You take the negative of g applied to x and d of x applied together. So all of that. Along with the definition, define d of x to be 0.00000001, like 0.00001. There we go. Like average stamp, deriv is a procedure that takes a procedure as an argument and returns a procedure as a value. For example, to approximate the derivative of x maps to x cubed at 5, whose exact value is 75, we can define cube of x to be x times x times x times x. Take the derivative of the cube at 5. 75.00, whatever. With the aid of deriv, we can express Newton's method as a fixed point process. Define Newton transform that takes input g. Procedure Newton transform that takes input g. The procedure that takes to be the procedure that takes x as input does x minus this term, and x. Divides g of x, derivative g. Okay. Define Newton's method g. Guess is the fixed point of Newton transform of g, and guess. The Newton transform procedure expresses the formula at the beginning of this section, and Newton's method is readily defined in terms of this. It takes as arguments a procedure that computes the function for which we want to find a 0, together with an initial guess. For instance, to find the square root of x, we can use Newton's method to find a 0 of the function y maps to y squared minus x, starting with an initial guess of 1. This provides yet another form of the square root procedure. To find the square root of x to be Newton's method with input lambda, y minus square of y, and x, y minus square of y squared minus x. Okay. The procedure that takes input y, that is the square of y minus x, starting at 1 is our first guess for x. Abstractions and first-class procedures. We've seen two ways to express the square root computation as an instance of a more general method, once as a fixed point search and once using Newton's method. Since Newton's method was itself expressed as a fixed point process, we actually saw two ways to compute square roots as fixed points. Each method begins with a function and finds a fixed point of some transformation of the function. We can express this general idea itself as a procedure. To find fixed point of transform that takes inputs g, transform, and guess. That returns fixed point applied to transform of g and guess. Transform applied to g and guess. Okay. This very general procedure takes as its arguments a procedure g that computes some function, a procedure that transforms g, and an initial guess. The returned result is a fixed point of the transform function. Using this abstraction, we can recast the first square root computation from this section, where we looked for a fixed point of the average damped version of y maps to x divided by y, as an instance of this general method. Define the square root of x. Define procedure square root of x to be a fixed point of transform applied to the procedure that takes input y that divides x over y, and does average damp to that, and then initial guess 1. Similarly, we can express the second square root computation of this section, an instance of Newton's method that finds a fixed point of Newton's transform of y maps to y squared minus x, as define square root of x to be this procedure square root that takes input x to be the fixed point of transform to be the procedure that takes input y that is y square of y minus x. Apply Newton transform at 1, starting with a guess of 1. We began section 1.3 with the observation that compound procedures are a crucial abstraction mechanism because they permit us to express general methods of computing as explicit elements in our programming language. Now we've seen how higher order procedures permit us to manipulate these general methods to create further abstractions. As programmers, we should be alert to opportunities to identify the underlying abstractions in our programs, and to build upon them and generalize them to create more powerful abstractions. This is not to say one should always write programs in the most abstract way possible. Expert programmers know how to choose the level of abstraction appropriate to their task. But it is important to be able to think in terms of these abstractions, so that we may be ready to apply them in new contexts. The significance of higher-order procedures is that they enable us to represent these abstractions explicitly as elements in our programming language, so that they can be handled just like other computational elements. In general, programming languages impose restrictions on the ways in which computational elements can be manipulated. Elements with the fewest restrictions are said to have first-class status. Some of the rights and privileges of first-class elements are: they may be named by variables, they may be passed as arguments to procedures, they may be returned as the results of procedures, and they may be included in data structures. Lisp, unlike other common programming languages, awards procedures full first-class status. This poses challenges for efficient implementation, but the resulting gain in expressive power is enormous.